Welcome to a session on ideal gas equation. In the session, we will be seeing Dalton's law of partial pressures, what are real and ideal gases, ideal gas equation, and also calculation or evaluation of the value of universal gas constant R. So, these are the topics we will be dealing in this session. Now, moving on to the topic, first we will be seeing Dalton's law of partial pressures. Now, according to Dalton's law of partial pressure, the total pressure of any mixture of gases, it has to be noted it is not an individual gas, it is a mixture of gases. The total pressure of a mixture of a gas is equal to sum of partial pressures of the constituent gases. I will make it clear, like if you are having a mixture of gases, it is not a single gas, it is a mixture of gases, important point to be noted, and let the gas be A and B. So, I am having a mixture of two gases, it can be more than that, but for simplicity's sake I am taking only two gases A and B. Now, if I take these two gases in a container, I am going to take it in a single container. Now, what will be the total pressure of this gaseous mixture? Will be equal to sum of partial pressures of A and B. So, to go into detail, first we will have to know what do you mean by partial pressure. So, we will just understand as such, that is the total pressure of a mixture of gases is equal to sum of partial pressures of A and B. So, that will be the Dalton's law. Now, partial pressure of gases in a mixture is the pressure of the gas which it will be exerting when it occupies alone. It is occupying alone the whole volume of the mixture at the same temperature. I will make it clear. Suppose I am having the mixture of gases A and B. So, this is a vessel which contains the mixture of gases A and B. Now, if I have to find out the partial pressure of A, what I will do is, I will have to put, though I am drawing a different one, there is the same vessel which has got the same volume. Okay. Now, in that same vessel I will put A alone, only A will be there. Now, if A alone is occupying this whole volume, what would be the pressure of A? That is known as partial pressure of A. It is denoted by small letter p with a suffix A to show that it is a partial pressure of A. In a similar manner, if I keep B alone in this volume, and what would be the pressure of the gas B in that case? That is known as partial pressure of B. So, I think it is clear, that is, if the gas alone occupies the whole volume and the temperature also should be the same, and what is the pressure exerted by that single gas in that whole volume? It is known as the partial pressure. So, this is the same as, suppose this is a volume V, I am considering V1, and this also should be volume V1. The same volume, if that individual gases they are occupying alone, that pressure is known as partial pressure. So, just again I will repeat it, partial pressure of a gas in a mixture is the pressure the gas would exert if it alone occupies the whole volume of the mixture at the same temperature. Now, partial pressure, how will you calculate partial pressure? Partial pressure of any gas, there is a small letter p suffix A, equals, this is mole fraction. It is denoted as chi A multiplied by P, where P is the total pressure. Okay. So, partial pressure of any constituent, if this is, in this case it is A, P A is equal to mole fraction of A, chi A multiplied by capital P, that is a total pressure. It is a product of mole fraction and total pressure of that particular constituent. Now, what is mole fraction? It is a fraction of that particular constituent, number of moles of that constituent to the total number of moles. Suppose here I am having more than 2 constituents, that is A, B, C, etc. The mole fraction of A is equal to, that is chi A will be equal to number of moles of A. ANA means number of moles of A. Okay, number of moles of A divided by, if it contains many number of constituent gases like A, B, C, etc., you take the total number of moles. This is the total number of moles. Okay. In total number of moles of that particular constituent, and that becomes a fraction, and this is known as mole fraction. This is mole fraction. And if I have to say it is a mole fraction of B, that is chi B is equal to, you have to take number of moles of B divided by total number of moles, that is Na Nb plus Nc plus how many are there? You have to take the total number, and out of total number, how many number of moles are there of B represents the mole fraction of B. Now, we will come back to the Dalton's law of partial pressure. Here we have told that the total pressure of the gaseous mixture of gases is equal to sum of the partial pressures of constituent gases. Suppose we are having a gas mixture containing number of constituents A, B, etc. Okay. The total pressure capital P is equal to partial pressure of A plus partial pressure of B and so on. It is the sum of partial pressure of individual gases, okay, where capital P stands for the total pressure, P A, P B, etc. They are the partial pressures of the constituents A, B, etc. Hope it is clear. Next, what we are going to see ideal gas and real gases. Real gases are also, I can mention them as non-ideal gases. So, gases we have two types, that is ideal gases and non-ideal, or we call it as real gases. Ideal gases means they are perfectly theoretical. You can have only an hypothetical gas which we can consider as an ideal gas. Real gases are those gases we find, that is oxygen, nitrogen, all those things, all gases, they are non-ideal and they are known as the real gases. Now, how will you identify whether a gas is ideal or not? Ideal gas is the one which obeys Boyle's law, Charles' law and Avogadro's law. It is not simply just obey, but under all conditions of temperature and pressure. Under all conditions of temperature and pressure, Boyle's law, Charles' law and Avogadro's law should be obeyed by the gas. Only then we can call that gas to be ideal, and this is imaginary, or you can say it is only a theoretical one, it does not exist. Now, what is a real gas? Real gas is also known as a non-ideal gas, is the one which does not obey ideal gas laws under all conditions of temperature and pressure. Thus, just the opposite of the first one. Now, how will you distinguish these two? We will just see the points. Now, first we will see what are the ideal. Ideal gas, it obeys Boyle's law, Charles' law and Avogadro's law under all conditions of temperature. It is not simply at a single temperature or pressure conditions, under all conditions, whether the temperature is high or temperature is low, pressure is high or pressure is low, immaterial. Under all conditions, the gas should strictly obey Boyle's law, Charles' law and Avogadro's law. So, such a gas is known as ideal gas. Now, the volume occupied by the molecules. Just note that it is the volume occupied by the molecules is negligible when compared to the total volume occupied by the molecules. There is a difference in these two, I will make it clear. volume occupied by the molecules means, if you consider a gas in a container, okay, you know that the molecules are very far apart. Now, this is the volume occupied by the gas, because the gas molecules, they are occupying such a big volume. Now, what do you mean by volume of the molecules, Okay. So, suppose the same volume if I take, and if I compress all these molecules, and this is the volume occupied by the molecules. These molecules altogether, they can sit in such a small space, and that is the only space that molecules actually require. But since they are far apart, they can occupy a larger volume, and this is the volume occupied by the molecules. Or you can say that you take up this volume, how much volume it takes here, you just add it up, or you can compress them to a small volume, and this will be the volume occupied by the molecules. While I take the gas, it occupies the whole container where the molecules are far apart. So, this is a volume required by the molecules. You can say that the volume required by the molecules is negligible when compared to the total volume occupied by the gas. See, the gas is occupying such a big volume. Actually, the molecules alone, they require only this much volume, and therefore, compared to this big volume, the volume occupied by the molecules is negligible. Hope it is clear. Another point is, there is no intermolecular forces of attraction between the gas molecules. For if a gas is ideal, the gas molecules, they not exert any attractive or repulsive forces. There is no intermolecular forces of attraction or repulsion or anything else. So, such is the case when we consider an ideal gas, no intermolecular forces of attraction, and these two are very important, because when we go for some deviations from gas laws, we will have to take into consider these 2 points. Now, and the last one, it is a hypothetical, just a theoretical one. You can say there is an ideal gas, but there is no example for that. There is no gas which obeys Boyle's law, Charles' law and Avogadro's law under all conditions of temperature and pressure. Now, let us see what do you mean by real gases. Real gases means they are all the ordinary gases we come along, like hydrogen, oxygen, nitrogen, helium, neon, argon, all those gases, they are real gases. Now, their condition is does not obey Boyle's law, Charles' law and Avogadro's law under all conditions of temperature and pressure. At certain conditions within a certain range of temperature or pressure, they may obey ideal gas equations, but not at all conditions of temperature and pressure. Second point is, the volume occupied by the molecules is not negligible when compared to total volume occupied by the gas. That is because we can see that when we have a gas, if it is at a higher temperature and lower pressure, when the temperature is low and we have a high pressure, the gas molecules will come closer. Now, when the pressure is high and temperature is low, that is the condition. I will just write it down. Pressure is high and temperature is low. Under these conditions, the gas molecules will be coming closer. Now, when they come closer, they are not very far apart, their volume will also be low. We know that as pressure increases, volume decreases. So, volume becomes, that is, volume occupied by the gas will be small. Now, from a smaller volume, when we have to remove the volume occupied by the molecules, it cannot be neglected. Okay. So, in this case, for a real gas, it is not the case. Now, there is intermolecular forces of attraction between the molecules. In real gases, there is intermolecular force of attraction between the molecules. All existing gases are real. The other case it was only an imaginary one or hypothetical one. All existing gases are considered as real gases. So, these are the difference between the ideal gas and a real gas. Now, we are going to derive ideal gas equation, and we know that ideal gas is a gas which obeys Boyle's law, Charles' law and Avogadro's law under all conditions of temperature and pressure. So, the ideal gas equation is derived by combining these three laws. Now, let us go for that. Now, Boyle's law, as we have seen, at constant temperature and mass, we have learned that pressure is inversely proportional to volume. I am just making it the other way, that is volume is inversely proportional to pressure. In both cases that is the same. So, volume proportional, inversely proportional to, that is 1 by P. Charles' law states that at constant pressure and mass, volume is directly proportional to temperature, because as volume increases, temperature also increases. I mean temperature increases, volume increases, and in Avogadro's law, at constant temperature and pressure, volume is directly proportional to N. Here we have made this adjustment just to see in all the cases you can see that it is in terms of volume being proportional, volume proportional to 1 by P, volume proportional to T, volume proportional to N. Now, what I am going to do is, I am going to combine all these together, that is volume proportional to 1 by P. So, I can put it as volume proportional to 1 by P again into volume proportional to T into volume proportional to N. Okay. So, I will just combine it, volume proportional to N into T by P. Now, what I am going to do is, I am going to introduce a constant which is, we will call it as a proportionality constant, but that constant is not simply proportionality constant. We are going to introduce it with another name, that is R, capital R, which is known as universal gas constant. Okay. So, R is the universal gas constant, and this R is taken as the proportionality constant, N into T by P. I am just rearranging it, I am taking P over here, you will have P V is equal to, I will put N in the beginning, R into T, and this equation, see here, it is P V is equal to N R T. And this equation is known as ideal gas equation, because it is derived from Charles' law, Boyle's law and Avogadro's law. Now, here what is R? It is a universal gas constant, and this universal gas constant R is for 1 mole of a gas. For 1 mole of a gas, and therefore, we multiply it with N, you have it for N moles, and without N that will be for 1 mole. If I put it P V is equal to R T, this means that this is for 1 mole of a gas. If I put N, you will have for N number of moles. Okay. Now, here this R is known as universal gas constant, and that too for 1 mole of a gas. Remember that, do not forget. Now, we have to evaluate, we have simply told R, we need, it is a constant. So, if I evaluate once the value of R, and that R can be remembered, and that is a constant value, and but the condition is that the R value depends upon the units taken. So, depending upon the units, R will be having different values. Now, how to evaluate? I will give some examples, rest we will do it, we will by heart it as such. We know that the ideal gas equation P V is equal to N into R into T. Now, I have to evaluate R, and therefore, I will keep R on one side and I will take N and T to the other side. When it goes to the other side, it goes to the denominator. So, I will get it as P V by NT is equal to R, retaining R on the right hand side, or I can put it as R is equal to P into V divided by N into T. Now, I am going to evaluate the value of R in SI units. Okay. Here the unit of pressure in SI units is 1.01325 into 10 to the power 5 newtons per meter square. Volume is equal to 22.414 into 10 to the power minus 3 meter cube. Now, how do we get the volume? Here we know that the volume of 1 mole from Avogadro's law, 1 mole, or I can call it as molar volume. The condition is STP, volume of 1 mole or molar volume at STP. We have learned it as 22.414 liters. Okay. Now, converting that into decimeter cube, meter cube, you have 22.414 into 10 to the power minus 3 meter cube. Okay. If I am taking the volume as 22.414 10 to the power minus 3 meter cube, and that is for 1 mole, naturally the value of N, that is, should be equal to 1. Okay. So, I am putting N is equal to 1. Therefore, I can take volume as 22.414 10 to the power minus 3 meter cube. Now, again the temperature should be the STP temperature, that is 273.15 Kelvin, or you can eliminate 0.15 or you can put it as 273 also, it is okay. Now, I am going to substitute these values and I am going to evaluate for R. R is equal to P is equal to 1.01325 into 10 to the power 5 newtons per meter square. V is equal to 22.414 10 to the power minus 3 meter cube, whole divided by N is equal to 1 and temperature is equal to 273.15 Kelvin. Okay. Now, here when I calculate that, you will be getting the answer as 8.314. Okay. This 8.314, now you can see here it is meter raised to minus 2 and here we have meter cube. So, this will result in the value of N, M. We have Newton. Okay. This Newton multiplied by meter is known as the joule, and therefore, that can be replaced as joule, and we have Kelvin at the denominator, N into M by K, this becomes joule, and this is K raised to minus 1. So, this is R equals 8.314 joules per Kelvin, and that is for 1 mole, and therefore, that is per mole, because here I forgot to write it as mole. So, that is mole raised to minus 1, and this is the value for the value of R in SI units, and remember these values are required, you will have to by heart it. It is 8.314 joules per Kelvin per mole, or you can find it in the Clark's table if it is allowed in the exam. Next, we have to find out the value in calories. 1 calorie is equal to 4.184 joules. Now, we know that 8.314 joules, that is a value in SI units, divided by 4.184 will give you 1.987 calories per Kelvin per mole, or in some cases they will put it as 2 calories per Kelvin per mole. That is an approximation, because 1.987 they are taking it approximately equal to 2. Similarly, if you put the pressure in atmospheres, volume in liters, you can calculate the value of R as R is equal to 0.0821 liter atmospheres per Kelvin per mole. Okay, I am not going to do it again. Okay, just this is a way we will be finding out. Now, let us move on to a problem. Calculate the density of a gas. The density of a gas was found to be 3.43 gram per liter, that is 1 liter weighs 3.43 gram. So, that is the density, it is the density. Okay. At 300 Kelvin and 1 atmosphere pressure, calculate the molecular mass of the gas. You are supposed to find out the molecular mass of the gas, and here we have been studying ideal gas equation, and in that equation we do not have a term molecular mass. So, I will take ideal gas equation, we will have to convert that into any form where you can have a molecular mass. Now, what we are going to do is, we know that P V is equal to nRT is the ideal gas equation. This is the ideal gas equation. Okay. Now, to get molecular mass, the only option is N, because N means number of moles, and number of moles N is equal to mass of a substance whole divided by molecular mass. Mass I can represent it as W and molecular mass at capital W. Okay. So, I can substitute N as W by M, where M stands for the molecular mass. Now, what I am going to do is, if I substitute that for N, you can find out molecular mass from that. So, you are getting one of the step cleared, that is P V is equal to W by M into R T. Here I have written as N. N means that is the number of moles is equal to W by M, small w by M. This is the mass and this is the molecular mass. Okay. Now, I have got so much, but again the problem is you do not have, no pressure is given here, you do not have, temperature is there, of course, temperature is given, 1 atmosphere pressure is given, but we do not have any other values, like we do not have the weight here. So, you cannot calculate. So, again what we are going to do is, let us convert this. What is density? Because it is the value given here, data is density is given 3.443 gram. So, density means mass by volume. You have learned in the school, like mass by volume is equal to density. So, I am going to write the expression density is equal to mass by volume. Now, from this expression you can convert that in terms of density, because here this is mass, this is volume. So, if I bring it like this, like P is equal to, okay, this is the mass by volume. Of course, the other things are there, capital M and R T. Okay. This mass by volume, I can consider that to be density D. Okay, D stands for density. Because the data is density, we will have to somehow convert that into the density term. So, here we have mass and volume, this becomes density. Okay. Now, this is not the equation we need it in terms of molecular mass, because we are asked to find out the molecular mass. So, we will convert that. So, here I will put it as density instead of mass by volume, I can put it as density into R T by M. Okay. So, that is what is done here. Now, what I am going to do is, I am going to rearrange it in terms of molecular mass. So, I will take molecular mass to this side and the pressure term to denominator. Here molecular mass will come to the numerator, m is equal to, okay, here itself, here m goes to the numerator, p comes to the denominator. So, d into R T by P. See, that is the expression we have got, m is equal to d R T by P, capital P, that is the pressure. Now, we have all these values given as data in the problem. Density is given as 3.43 grams per liter, pressure is equal to 1 atmosphere, R is equal to 0.0. Now, since pressure is given in atmosphere, I will take the value of R as 0.0821 liter atmospheres Kelvin per mole. Temperature, it is given 300 Kelvin. Now, I can substitute all these in this equation. M equals density 3.43 grams per liter into R 0.0821 liter atmosphere Kelvin per mole into temperature, that is 300 Kelvin, whole divided by no need of division, no, density, pressure is there, 1 atmosphere. Okay. So, by calculating, you will get the value as 84.4809 gram per mole. Now, how the unit comes? Here gram is there, here liter is there, here liter, here another liter, get cancelled. Okay. Atmosphere and atmosphere get cancelled, Kelvin and Kelvin gets cancelled. Okay. The remaining is gram and mole inverse. So, the answer is 84.4809 gram per mole, and this is the molecular mass of that gas. Now, we will conclude, like in the session we have been seeing Dalton's law of partial pressures, where we learned that the total pressure is equal to sum of partial pressures of individual constituent gases, that is capital P is equal to P A plus P B plus so on, where the constituents are A, B, etc. Next, we saw ideal gas and real gases and their difference between the ideal and real gases. Ideal gases are simply hypothetical, while all existing gases are real gases. Then we saw the ideal gas equation, and ideal gas equation, it is an ideal gas which obeys Boyle's law, Charles' law and Avogadro's law at all conditions of temperature and pressure, and therefore, we derived ideal gas equation from Boyle's law, Charles' law and Avogadro's law together combining. We get the expression as P V is equal to nRT, where P stands for the pressure of the gas, V the volume of the gas, small n is the number of moles, capital R is known as universal gas constant, and T is the temperature in Kelvin scale. Next, we evaluated the value of R in different units. In SI units, R is equal to 8.314 joules per Kelvin per mole. In calories, it is 1.987 calories per Kelvin per mole, and in liter atmospheres, it is 0.0821 liter atmosphere per Kelvin per mole. And that is all for this session. Thank you.